Okay, sorry about the wait. Let's get started. Today we are going to discuss, we're going to continue our discussion on spatial acceleration structures. Last week, we introduced a couple of simple spatial acceleration dial structures, like the uniform grid dial structure and bounding volumes. In the case of bounding volumes, we try to make raycasting operations more efficient by approximating complex objects with simpler geometric primitives. And the hope is that performing intersection tests against the simple geometric primitives will be much more efficient compared to performing intersection tests against the more complex objects. In the case of bounding volumes, we're still performing the same number of intersection tests. We still have to perform one intersection test for every object in the scene. But by approximating the complex objects with simpler geometric primitives, the hope is that each of those intersection tests can be made more efficient. In today's lecture, we're going to take a look at more sophisticated data structures that take these simple structures that we have discussed so far and then extend them in order to make these raycasting operations even more efficient. The next data structure that we're going to look at will be bounding volume hierarchies. And the idea with bounding volume hierarchies is that we can use bounding volumes to approximate groups of objects at a time instead of just using bounding volumes to approximate individual objects. As we mentioned before, with bounding volumes, we still have to perform the same number of intersection tests for every ray that we cast into the scene. But one idea with bounding volume hierarchies is that we can use bounding volumes to also reduce the overall number of intersection tests that we have to perform. And the way that we are going to do this is by approximating groups of objects using a single bounding volume. For BVHs, the way that we are going to organize these bounding volumes will be to construct hierarchies of bounding volumes that approximate smaller and smaller groups of objects. For example, in this scene, we have 6 different objects. And we can approximate this entire scene with one large bounding volume that contains all of the objects. Now, whenever we have to perform a raycasting operation to the scene, we can check for intersections between our ray and this large bounding volume that encompasses our entire scene. If the ray misses this bounding volume, then we can safely ignore all of the objects inside because the ray is guaranteed to not intersect with any of the objects inside our volume. And this can potentially allow us to drastically reduce the total number of intersection tests that we have to perform. Now, once we have this large bounding volume that contains all of the objects in the scene, we can then hierarchically partition this bounding volume into smaller and smaller bounding volumes that each contain a smaller and smaller group of objects. For this large bounding volume A, we can split this bounding volume into 2 children bounding volumes, B and C. In this example, bounding volume B will end up containing the 4 objects on the left, and then bounding volume C will contain the remaining 2 objects on the right. And we can repeat this process recursively. So we can recursively split the number of objects inside a bounding volume into smaller and smaller groups, and then we can fit bounding volumes to each one of those groups. And we can repeat this process recursively until we get down to bounding volumes that contain some minimum number of objects. So for example, in this simple scene here, we might stop partitioning the bounding volumes once we are down to, let's say, 2 objects per bounding volume. So in this case, bounding volume B contains 4 objects. So we can split that bounding volume into 2 bounding volumes that each only contain 2 objects each. And at that point, every bounding volume only contains some minimum number of objects, and we can stop partitioning the bounding volumes. What this gives us then is a hierarchy, a tree of bounding volumes, where every parent node represents a bounding volume, and that bounding volume can be split into smaller children bounding volumes. And the way that we can use these BVHs to accelerate ray intersection tests is that we are always going to perform intersection tests against the parent bounding volume first. If we miss the parent bounding volume, then we can safely ignore all of its children. If we intersect the parent bounding volume, then we have to expand the parent bounding volume and perform some additional intersection tests against the children of the bounding volume. And we repeat this process recursively until we either find no intersections or we find some intersections with the objects inside those bounding volumes. Okay. So let's go through an example of how we construct these BVHs. Given a scene that contains some number of objects, we're going to first construct a large bounding volume that fully contains all of the objects in the scene. And this will represent the root bounding volume of our hierarchy, which contains all of the objects. Next, we'll split up this bounding volume into 2 halves. So for example, we might split the objects into a left group and a right group. And then we can fit bounding volumes to each one of those smaller groups of objects. We can then recursively, again, split each one of those bounding volumes. For the left bounding volume, maybe we can divide the objects in terms of a top group and a bottom group. So that will then give us, let's say, 2 additional bounding volumes like this. Similarly, the bounding volume on the right, we can also split that into a top group of triangles and a bottom group of triangles. And that might give us another 2 additional bounding volumes. Now, so we'll repeat this process recursively until every bounding volume contains some minimum number of objects, in which case we can stop and then return the hierarchy of bounding volumes that we've constructed. Okay, so any questions about this process of how we construct this hierarchy of bounding volumes? Okay.
Regarding when we do a retesting, is it, let's say I want to run across and hypothetically it'll hit all of the boxes.
Yep.
It will only consider the first one that's correct.
Oh, no, we actually have to check every single bounding volume that the ray intersects with, and we'll discuss some reasons why that's the case.
But I send out in every single one, so then
you have to check all of them then. Yeah, and there will be some reasons for why we have to do that, and we'll talk about that in the next couple of slides. Okay, but any questions about how we construct these bounding volumes? Right, so the key idea is just that we take, yep.
Is the decision to split up right of that arbitrary?
Yeah, so it's a heuristic that we have to decide on, and how we do that splitting is a design decision that we do have to make when implementing BVHs, and we talk about some of the different design choices that you can make in the next few slides. Yeah, but for now, just assume that we have some method that tells us how to split up the objects into 2 different groups. So with BVHs, we just take large groups of objects and we split them into smaller and smaller groups. So as the previous question, oh, right. Now, one thing to note about the construction of these bounding volumes is that the bounding volumes themselves can potentially overlap. For example, for the 2 bounding volumes on the right side of the scene, we have a top bounding volume that contains 3 objects, and then we have a bottom bounding volume that contains 2 objects. And these 2 bounding volumes actually overlap with each other. So when we take a bounding volume and we split it into 2 children volumes, it's possible for the two volumes to overlap. But the key property that we need to maintain when splitting the bounding volumes is that every object can only belong to a single bounding volume. An object cannot belong to multiple bounding volumes at the same level of the hierarchy. So whenever we take a parent bounding volume and split into two children, we have to make sure that every object belongs to only one of the children volumes. And depending on how we how we split up the objects, we might end up with bounding volumes that overlap each other. So for some of these triangles, some of the triangles, they intersect both bounding volumes, but the triangles will still only be assigned to one particular bounding volume, never two. Another characteristic of these bounding volumes is that, again, they have to fully contain all of the objects that belong to the bounding volume. So every vertex for every object in the scene has to be fully contained within the bounding volume that it belongs to. Okay, as alluded to by the question earlier, one of the key design decisions that we have to make when constructing BVHs is, given a bounding volume that contains some number of objects, how do we split up that bounding volume into two children bounding volumes? In other words, how do we take a group of objects and split it into two smaller groups? And the way that we partition a bounding volume can have a very big effect on the overall efficiency of the data structure. A bad partitioning of the objects into two groups can end up leading to a data structure that's not much more efficient than not having any bounding volumes at all. Now, the ideal partitioning that we want for a group of objects is that we want to divide up the objects in a way that they form nice compact clusters and that they lead to a balanced tree when we construct this hierarchy of bounding volumes. Now, unfortunately, trying to find the optimal partitioning for a group of objects that gives us the most balanced tree as well as the tightest, the most compact clusters. Unfortunately, this is an NP-hard problem. So we can't efficiently compute the optimal partitioning for bounding volume. And therefore, in practice, we often have to rely on heuristics to try to give a reasonable partitioning of groups of objects. On the screen here, I've listed a bunch of commonly used heuristics in practice. And let's go through each one of these heuristics to see how they might work. So one very simple heuristic we can use is that given a bounding volume, we can just split that bounding volume in half and then divide up the objects accordingly. For example, I can take this large bounding volume, I can just cut it down the middle, and then all of the objects that lie on the left side of this bounding volume will form one group. And then all of the objects that on the right side of the bounding volume can form a different group. And this then leads us to two new children bounding volumes for each group of objects. So the center partition heuristic is very simple and efficient. You can implement it very efficiently. But the drawback with this simple heuristic is that it can often lead to very unbalanced trees when we construct this BVH. The center partitioning heuristic works well if the objects are more or less uniformly dispersed in the scene. So in this case, simply dividing up the scene in half will give us relatively similar number of objects for each children bounding volume. But if we have a very non-uniform distribution of objects, let's say if all of the objects are cluttered on the right side of the scene, then if we simply partition the scene in half, then chances are most of the objects will end up being in one bounding volume, and then the other bounding volume will end up having very few objects. And this can then lead to a very unbalanced tree where we are going to end up with a tree that with a very large depth. And this will end up leading to lots of unnecessary intersection tests when using the resulting BVH. So similar to a binary search tree, ideally we want the BVH to be as balanced as possible. So we want to be able to partition the objects into relatively similar size groups. So an alternative heuristic that we can use that can give us slightly better, slightly more balanced trees is to use the median partitioning heuristic. With this particular heuristic, we're going to take all the objects in the scene, and then we're going to project them onto one coordinate axis. For example, let's say we are going to split the volume along the x-axis. Then we're going to take all the objects, and then we're just going to project them onto the x-axis. So we're going to get the x-coordinate of all of these objects, and then we're going to pick the median coordinate that splits all the objects into two different groups. So for this simple scene here, we might get a split that looks like this. And once we have this partitioning of the bounding volume, we can just assign all of the objects on one side of the split to one bounding volume, and then all the objects on the other side of the split is going to belong to a second bounding volume. And this can help us construct more balanced trees that that contains a more balanced number of objects per child. Okay. One slight drawback with this median partitioning heuristic is that it's a little bit more expensive to implement. So in order to compute a partition, we might have to, let's say, sort all of the objects along some axis before we pick the median coordinate to partition the scene. So this is a little bit more expensive compared to the center partitioning heuristic, but it has the advantage of giving us more balanced partitions. Yeah, any questions about these heuristics? Nope.
Are these heuristics like one? So the 3D scene, like the 3D when we could put it up. So did we use that kind of information sometimes?
Right. So for computing which axis to determine which axis to partition the scene on, you might just alternate between the three different axes. Oh, yep. Yeah, it depends on the application. Constructing these data structures can often be fairly expensive, so you might not be able to update the data structure every frame. So oftentimes you might just pre-compute the data structure beforehand and then just reuse it over and over again, assuming that your scene doesn't change too much. Any other questions? With this median partitioning heuristic, we can get more balanced trees where each children bounding volume will contain a similar number of objects. But the drawback with this approach is that it might not necessarily give us very compact bounding volumes. So depending on how the median coordinate splits up the objects into different groups, we could potentially get bounding volumes that are not very compact. So they might contain a lot of empty space. And similar to the issue with bounding volumes that we discussed in the previous lecture, the more empty space that we have in a bounding volume, the more false positive tests we can get. Good. So these simple heuristics generally work well if you have relatively simple scenes where the objects are fairly uniformly distributed in the scene. But for more complex scenes, in practice, the BVHs will often rely on more sophisticated heuristics to get better partitionings of a bounding volume. Now, in practice, there are lots of different heuristics that you can use. In this lecture, we're just going to give you an example for more sophisticated heuristic that we can use to compute a good partitioning of a bounding volume. So one example of such a heuristic is called the surface area heuristic. And the idea with the surface area heuristic is that they want to try to construct a partitioning of a group of objects in a way that minimizes the expected cost of performing ray intersection tests. And the way that this method does this is by using a property of bounding volumes, which says that, let's say if you have two bounding volumes, a bounding volume A, which contains a child bounding volume B. Now, if we have a ray that intersects with the parent bounding volume A, the probability that the ray is going to also intersect the child bounding volume B is going to be proportional to the surface area of the child with respect to the parent. So let's say if I have a very large child bounding volume that has a similar surface area as the parent bounding volume, then any ray that intersects with the parent is going to have a very high likelihood of also intersecting with the child bounding. On the other hand, if the child bounding volume has a much smaller surface area compared to the parent bounding volume, then any ray that intersects with the parent will still have a relatively low likelihood of intersecting with the child. And we can use this ratio to estimate the cost of performing intersection tests given a particular partitioning of the bounding volume. So the way that we apply this heuristic is that we are going to define a cost function. The input of the cost function is going to be a partitioning of a specific bounding volume into two different halves. So V is going to be our parent bounding volume. And then L and R represents the two children bounding volume that's constructed by particular partitioning of the objects in V. So given V, we're going to split the objects into two children bounding volumes. And then we're going to compute a cost for this particular partitioning of the bounding volume. And the surface area heuristic is going to compute the cost according to this formula here. And we are going to go through each one of these terms to take a look at what they represent. So given a particular partitioning of the bounding volume, we're going to compute the cost, and this cost is going to be given by a number of variables. KT represents a constant cost for traversing through a bounding volume. So this might be a ray that's going through a bounding volume, and we might have to perform, let's say, intersection tests between that ray and the children bounding volume. So KT is a constant cost that we have to pay. This is not something that we can really change depending on the partition. But what we can change is going to be the second term in this cost function. So in the second term, we have a constant value, Ki. This represents the cost of performing an intersection test against all of the objects that are contained inside the bounding volume. So let's say if inside our bounding volume, we have a bunch of triangle meshes. Ki might represent the cost of performing a ray intersection test against a triangle. Okay. And then we're going to have a bunch of terms that depend on the ratio of the surface areas between the children bounding volume and the parent bounding volume. So first we have the ratio between the surface area of the left child with respect to the surface area of the parent V. And then this is multiplied by the number NL, the number of objects that's inside the left child bounding volume. So the way to interpret this is that the surface area between the two bounding volumes tells us if a ray intersects with the parent bounding volume, what is the likelihood that the ray is going to also intersect with the left child bounding volume? So this tells us the likelihood that we're going to get an intersection with the left child. And if we have an intersection, NL times Ki represents the cost that we are going to have to pay for performing all the intersection tests against the objects inside the bounding volume. So this term tells us what the expected cost of what the expected cost is of that particular partitioning. So what's the probability that we intersect with the left child? And if we intersect with the left child bounding volume, what's the cost of performing the intersection test against all of the objects inside our volume? And similarly, we have a similar term for the right child bounding volumes as well. So we have the ratio of the surface area of the right child with respect to the parent, which tells us the likelihood of intersecting with the right child. And this is multiplied by the number of objects inside the right child, which tells us what the cost of performing intersection tests against all of the objects inside the right child is going to be. So given a particular partitioning of a bounding volume into two halves, we can evaluate this cost function, which would tell us how good that particular partitioning is. And the way that we apply this cost function is that we take a parent bounding volume and we have some heuristics that proposes possible partitionings of that bounding volume. So you might use, let's say, the median heuristic or the center partitioning or the center heuristic. So we want to generate a bunch of possible partitionings of the bounding volume. And then for each one of those candidate partitions, we are going to evaluate the cost according to this cost function. And once we have the cost for every single partition, we will just pick the partition with the minimum cost, and then we'll move on to the next partition. So we just split up the volume. We just pick the best partition according to this cost, and then we just apply the cost function recursively to split the children's into smaller and smaller volumes. So we can just apply this cost function greedily to every single bounding volume in order to find a good partitioning of those volumes. It's not going to give us the optimal partitioning, but in practice, it gives us a good enough partitioning that's reasonably efficient in practice. Okay, so this is one example of how you can apply these cost functions to try to pick better partitionings of a bounding volume. And in practice, you can come up with other cost functions as well, depending on your application. Any questions about this?
John, but between like this, it's the same thing as a random array from outside the box, from to a random direction, as long as it goes through the box.
Yeah. So this doesn't take into account maybe what direction the ray is coming in. It just kind of assumes that the ray might come in at any direction.
And like adding on to that, do they have to be boxes?
Oh, yeah, BVHs, they don't have to be boxes. You can select any geometric primitive you want for your bounding volume. Just boxes in practice tends to work quite well.
Does this heuristic still hold true for the theorem for other chains?
Also, what?
Does the theorem for the heuristic still hold true for other chains?
Yeah, you can apply this cost function to other shapes as well. It just requires you to compute the surface area. Any other questions? Okay. Now, once you have constructed BVH, let's take a look at how we use a BVH to perform ray intersection tests. In this example, we have a scene with a bunch of triangles. And let's say we cast a ray that passes through the scene in this particular direction. And we now want to try to use a BVH to detect the closest intersection with our ray. We're going to start by first checking for intersections between the ray and the root bounding volume, which contains all of the objects in the scene. If the ray misses this bounding volume, then we got lucky and we can safely ignore all of the objects. We don't have to perform any additional intersection tests. But if the ray intersects with this bounding volume, then we're going to have to expand the bounding volume and test for intersections against the children bounding volumes of that root node. Let's say for this BVH, we intersect with the root bounding volume. So now we have to test against the children. And let's say the children bounding volumes end up splitting the objects into a left half and a right half. In this case, the ray, we're going to check for intersections between the ray and the two children bounding volumes. the ray is going to miss the left child, so we can safely ignore all of the objects on the left side. But the ray is then going to intersect with the right child, and we'll call this bounding volume 1, which means that we now have to go and expand the right child bounding volume and check for additional intersections against the children of that bounding volume. For this right bounding volume, let's say we split up the objects into a top half and then a bottom half. So we might have 2 additional bounding volumes like this. The ray is going to intersect both bounding volumes. So we're going to have to, again, expand both bounding volumes and check for additional intersections. So let's say we expand the top bounding volume first. We're going to expand this bounding volume. And then at that point, we reach the root. So we reach one of the leaf nodes of the BVH. Once we've arrived at the leaf node, then no additional bounding volumes, and we will have to perform the more expensive intersection test against the objects that are contained within that bounding volume. So in this case, we have to perform some intersection tests against 3 triangles inside that child bounding volume. When we perform these intersection tests, we're going to find one intersection. We're going to find one intersection with this particular triangle here. Now, one thing that you have to be careful of is that the first intersection that you find in a BVH is not guaranteed to be the closest intersection. So even though we found this intersection with the triangle, it's not guaranteed to be the closest intersection. So we still have to go back and check for additional intersections against other bounding volumes. Since this ray intersects with both the top bounding volume and the bottom bounding volume, we are going to have to expand the bottom bounding volume and then check for additional intersections. The bottom bounding volume contains 2 triangles, so we're going to perform 2 triangle intersection tests. In this case, we find a second intersection, which is this other triangle here. And at this point, we've performed all the intersection tests that we need to perform, and we can go and return, let's say, the closest intersection. In this particular example, the first intersection that we found turned out to be the closest intersection. But this in general is not guaranteed. In a BVH, because the bounding volumes can overlap with each other, and because an object can intersect with multiple bounding volumes, the first intersection that we find may not be the closest intersection. So we do have to go through and find all of the intersections before we return the closest one. Even though the first intersection we find is not guaranteed to be the closest intersection, one of the nice characteristics of a BVH is that we are going to, at most, check for intersection tests against every object inside the bounding volume, at most once. And this is because of every object is only going to belong to one bounding volume at a particular level of the hierarchy. So even though we might have to perform intersection tests against many bounding volumes, when it comes to the original objects that are contained in the scene, we are going to at most test against every object at most once. And this is a really nice characteristic because the objects inside the bounding volumes could potentially be very complex. They could be a very complex triangle mesh that contain lots and lots of triangles. And because we only ever have to test against an object at most once, this helps to helps us to reduce the cost of performing the more expensive intersection test against the original objects. Okay. So this is an example of how you can use a bounding volume hierarchy to make ray intersection tests more efficient. Any questions about this?
Okay, looking back a little bit again. If all your objects happen to be like rectangles,
yep.
With BVH providing that.
Even if all of your objects are boxes, your BVH can still lead to some efficiency improvements because you can still approximate multiple boxes with just a single box. So that can help you more efficiently. Let's say, remove groups of objects at a time. Any other questions? Okay. Now, so BVHS is an example of a hierarchical object partitioning data structure, where the data structure will divide up the scene in terms of groups of objects. So next we're going to so the next data structure that we're going to look at will be a hierarchical space partitioning data structure, where instead of dividing up the scene in terms of groups of objects, we're going to hierarchically divide up the scene in terms of the space that's inside the scene instead. And KD-JIS will be one example of this kind of hierarchical space partitioning data structure. We probably don't have enough time to go through this today, so this might be a good point to wrap up for this lecture, and then we'll finish the rest in Friday's lecture. But I guess any questions before we wrap up for today? Okay, if nothing else, then I'll see you on Friday.